Good day, everyone. So, today this is our first video on our YouTube channel, Pharma Engineering. So, the topic that we have selected is evaluation and estimation of condenser heat transfer area. It's nothing but checking the adequacy of a available condenser for a specific process. And the second part is going to be about estimating the heat transfer area of a condenser based on the reactor capacity. So, before going into the topic, let's see the basics. So, here we got total three phases: the gas, liquid, as well as solid. So the horizontal axis indicates the temperature, and the vertical axis, the y-axis, indicates the change in phases. So here we got total three things: the solid phase, liquid phase, as well as gaseous phase. So the first thing that we have to understand while going into calculation is what does exactly sensible heat and latent heat means. So sensible heat refers to the energy which is required for change in temperature of a specific component, whether it can be solid or it can be liquid or it can be gas. So without having any change in phase, so what is the amount of energy required to have only temperature change? It refers to sensible heat. Whereas coming to the latent heat, so it is going to be a reverse thing, like the energy required only to have a phase change without any temperature change. So it can be referred as latent heat. So in short, sensible heat refers to change in temperature without phase change, while latent heat refers to phase change without any temperature change. So this is the major difference. So for estimating this sensible heat as well as the latent heat, so we'll be using two different formulas which are being commonly used. So in order to estimate the sensible heat, so we are going to use the formula mcp delta T, and while trying to estimate the latent heat, we have to use the formula m lambda. So now we have to see the notations one by one. So m refers to the mass flow rate. Why? Because if it's a continuous process, so m refers to mass flow rate. If it's a batch process, m refers to the mass. And cp, it refers to specific heat. And dt refers to the change in temperature. And lambda refers to latent heat of evaporation. So these are the basic things we'll be using to estimate the sensible heat as well as the latent heat. So while estimating a heat load, so we are going to use both the parameters. So heat load can be estimated by using the formula mcp delta T plus m lambda. So based on the requirement, we are going to calculate these things, whether it can be sensible heat or it can be only the latent heat. So these things we have to understand before going into the topic. Now let's see what is exactly and how does exactly we need to estimate these loads. So we'll take the case of a reactor. So generally this is how a reactor will look like. So let's say this is a reactor and this is the reactor's jacket. And let's say there are some reactor contents inside the reactor. So let's say it's a reaction mass, it's a combination of multiple components. So there is certain amount of reaction mass inside the reactor, and whether if you are going to make any change with respect to temperature, or if you want to vaporize the solvent or the volatile content present in the reaction mass, so it needs some amount of heat. Or sometimes if you want to cool the reaction mass from higher temperature to lower temperature, so in such a case we need certain amount of heat which need to be taken out from the system. So the reactor shall be referred as the system, and the energy which is required, or the energy which need to be taken out from the system, shall be referred as the demand. So demand refers to energy required, or energy which need to be taken out from the system. While coming to the next one, that is nothing but the supply. So supply refers to the energy which is going to be transferred from the reactor jacket to the reaction mass. So whether if you are going to supply the energy to the reaction mass, or if you are going to withdraw the energy from the reaction mass, so it is nothing but the supply. So energy required, or energy which need to be taken out from the system to the jacket, shall be referred as the supply. So using this, both the demand as well as supply, we are going to perform the energy balance. So in order to estimate a certain heat load, so we are going to use the both things, the demand as well as the supply. So demand refers to the requirements of a system, nothing but the requirements of a reaction mass, whether it can be heat input or heat withdrawal. While coming to supply, while coming to supply, so the amount of energy which need to be taken out from the system, or which need to be provided to the system, shall be referred as supply. So in order to estimate the demand and supply, so we will be using the formulas m cp delta t, or m lambda, or sometimes it is going to be both. It depends upon the case, m cp delta t plus m lambda. So both can be used. While coming to supply, so we are going to use UA LMTD. Okay, so these are the two equations which we are going to use while performing a energy balance. So now coming to our case, that is checking the adequacy of a condenser which is already available. So whether it is required to perform a specific operation or not. So first of all we have to evaluate, and the second case is going to be about estimating the condenser heat transfer area for a specific reactor capacity. So let's take a case where, so let's check here. So the case is going to be, we need to estimate the heat transfer area required to condense a boil-up of toluene. So let's say the boil-up is around 500 liter per hour. Okay, and we got a condenser capacity of 5 meter square. So in this case, we need to estimate the area of condenser capacity required to condense the boil-up of 500 liter per hour of toluene. So this is the case, like we already know what is the demand. So just we need to understand the supply. Okay, in the supply equation, that is UA-LMTD. So the only thing that we need to find out is the heat transfer area. So let's make a note of everything. Like the boil up rate is around 500 liter per hour. Though the solvent is toluene. So the density of toluene is 0.87 kg per liter. The latent heat of toluene is around 90 kilocalorie per kg. Okay, so as we know the boil up, first of all we have to estimate the heat load required. So here in this case it's a boil up scenario, that means it's already in vapor phase, the only thing that we need to do is we have to condense it. So in order to condense, so basically it's referred to a change in phase. So we have to use the formula of the latent heat. So here the case is estimation of heat load, and the heat load refers to only latent heat. So we will be using the formula m lambda. So we know the volumetric flow rate, that is 500 liter per hour. So we know the density and we know the latent heat. So in order to convert the volumetric flow rate, so we need to multiply it with the density. So volumetric flow rate multiplied with density gives us the mass flow rate, and again we have to multiply this total mass flow rate with the latent heat. So it will give us the heat load required. So this is going to be in terms of kilocalorie. So this is per 1 hour, kilocalorie per hour. And now we have to estimate, or we have to check the adequacy of a condenser. So already we got a 5 m square condenser. We have to understand whether it is going to suffice the case or not. So here in this case, we have to estimate the supply. So in order to understand the supply, so first of all we have to check what type of utility is available, whether it's a chilled water or it's a RT water or it's a chilled brine. So I'll be taking the case of a chilled water. So utility used is chilled water. So the supply equation is UA LMTD. Okay. So the inlet temperature of utility is, I'll take it as 8 degrees centigrade, and utility out I'll be taking it as 14 degrees, a delta T of 6 degrees. So here in this case we got a toluene as solvent. So first of all I'll try to understand the case as a normal distillation. So at normal conditions the solvent will boil at 1 atmosphere pressure. So the boiling point of toluene is 110 degrees centigrade. So basically there will be two types of distillations. One is vacuum and the second one is normal distillation. So here in this case we are going to discuss the scenario of a normal distillation. Okay. So the boiling point is 110 degrees, and now we have to estimate the LMTD. So coming to LMTD. So why we have to perform LMTD and why not delta T? So it's one of the topic. Let's try to discuss it after completion of the calculation. So as of now we are going to perform the calculation as per the given formula, that is UALMTD. So here in this case the boiling point of toluene is 110. Since it's in gaseous phase, the inlet temperature as well as the outlet temperature will remain same. Okay. Whereas coming to the utility, the inlet temperature is 8 degrees and outlet temperature is 14 degrees. So the LMTD shall be estimated as, so 110 minus 8 minus of 110 minus 14, right, divided by ln of, again the same thing, 110 minus 8 divided by 110 minus 14. So the LMTD is around 98.96 degrees. So out of this total UALMTD, we know the LMTD. So coming to U, so U refers to the overall heat transfer coefficient. Okay. So basically the overall heat transfer coefficient depends upon the thermal conductivity of the material through which we want to perform the heat transfer. So if it's a SS316 MOC for a specific condenser, so we are going to take the overall heat transfer coefficient in range of 400 to 500 kilocalorie per hour meter square degree centigrade. So here in this case I will be taking it as 400 kilocalorie per hour per meter square degree centigrade. Okay. So now we know U and we know LMTD. So we have to calculate the area A. In order to do that, we have to perform the energy balance. It is nothing but equating both demand as well as supply. So we are going to do demand equals to supply. So here the demand is 39,150 kilocalorie per hour, while coming to supply it is 400. U, A is we don't know, and LMTD is 98.97. so we need to equate both, and now A equals to 39,150 divided by 400 into 98.97. So if you are able to see, the heat transfer area required theoretically is around 1 m square, but whereas in this scenario we got a heat transfer area of 5 amp square condenser. So we can say the available condenser capacity is adequate. So this case refers to a non-boil up. Like here the boil up is already known. So if you want to estimate condenser capacity for a reactor of known capacity, of a specific reactor capacity, so what we have to do? Why? Because in this case I know that we got a solvent as toluene. If in a case if we don't know the solvent, so what we have to do? So this remains a question for many guys. So whenever you are going to map, or whenever you are going to procure a condenser for a specific reactor capacity, then simply we have to consider the reactor heat transfer area. So the second case is estimating condenser heat transfer area for a specific reactor capacity. So in this case, simply the condenser heat transfer area should be equals to the heat transfer area of reactor. So try to calculate the heat transfer area of reactor and then try to procure a condenser having a same amount of heat transfer area. Why? Because as a part of energy balance. So let's say using the same reactor which we have drawn. So this is the heat transfer area. Okay. So this is the heat transfer area. That means you are going to supply heat through this heat transfer area. So in this case, what will happen is the amount of energy that you are going to provide through this heat transfer area will try to heat up the reaction mass. So once the reaction mass is heated up, automatically the energy which is being transferred will be used to vaporize the volatile content present in the reactor. So that means the energy that you are going to transfer towards the reaction mass is taking the form of a liquid. I mean, it is being transferred to the liquid, and this liquid is going to carry the heat and it will try to convert into gas. So whatever the energy that we are going to give, it is trying to vaporize the liquid into gaseous phase, and at the condenser end we are going to take out the same amount of heat which is being given from the reactor. So ideally, if you are able to provide the same amount of heat transfer area which is available at the reactor, so in such a case what will happen is, so if you are able to provide the same amount of heat transfer area at a condenser, like what is exactly the reactor is having at a specific point of time, so it is adequate. Or in terms, or in other terms, so the amount of heat transfer area which is available to the reactor shall be provided at the condenser end also. So ideally, now let's take the case of a LMTD. So why does exactly we need to calculate the LMTD and why not delta T? So basically there will be three phases: solid, liquid as well as gas. So here in this case we'll try to estimate the LMTD for liquid as well as gas. So whenever the flow is in opposite direction, we will be referring it as counter current flow, and if the flow of utility as well as the reaction mass or the product content is in same direction, we will be referring it as a parallel flow or co-current flow. So here in this case I have taken it as a counter current flow. So the first scenario that we need to take is both the utility as well as the product is in same phase. Case 1, product and utility are in same phase. Okay, now let's see. So the same phase refers to liquids, let's say. So now the case is about estimating the LMTD, and we have to understand in what scenario we have to use LMTD and what scenario we have to use the delta T. So I'll consider total 3 cases are in gas phase. Case 3 refers to product and utility are in different phases. So these are the 3 scenarios that we have to understand. So coming to the first scenario, so if I want to perform heat transfer when the product as well as the utility are in liquid phase, so let's say this is the product flow and this is the utility flow. So in this case what happens is, if both are in liquid phase, so automatically from point to point there will be some variation. Like let's say initially the product is at 40 degrees and I'm going to heat up to 50 degrees. So let's say it is at 45 and from here it came up to 50 degrees. While coming to utility, so let's say utility is previously at 80 degrees, I'm going to take it as 78 degrees and here I'll be taking it as 76 degrees. So in this case what will happen is, we are going to heat up the product layer from 40 to 50 degrees and we are going to pass the utility from 80 degrees. So the utility is going to like the utility outlet is going to be at 76 degrees in this scenario. So in order to estimate the temperature difference, so it is going to be a difficult scenario. Why? Because from point to point, automatically the temperature is going to vary. Okay, as there is a variation from point to point with respect to temperature, so it is not possible for us to take the delta T. So in such a case, we need to estimate the log mean temperature difference. Why? Because as it is having temperature difference from point to point, we need to estimate the delta T using the log mean temperature difference, the LMTD. Okay. While coming to the next case, that is the product and utility are in gas phase. So I'll take the scenario where I'm going to boil toluene using steam as utility. So once the temperature of reaction mass reaches the boiling point of toluene, that is 110 degrees, automatically the boiling will start. So in such a case, so the boiling point of toluene is 110 degrees in the initial step, and in the next step also it's 110, and in the later step also it remains as 110. Why? Because as it's a gaseous phase, the temperature will remain same. Now coming to the utility, as I'm going to use steam, I'll take the steam is at 140 degrees. So the inlet temperature is 140, and at some point of length it is 140, and after at the end of the length also it is at 140 degrees. So in this case what's happened is, as it is in gaseous phase, so we are going to utilize the latent heat of steam. As we are going to utilize the latent heat of steam only, so the temperature will remain same. So in this case we can use the delta T. Why? Because the temperature is uniform throughout the length in both cases. And now let's come to the third case, that is the product and utility are in different phases. So here in this case what will happen is, I'll take the product is in liquid phase and the utility is in gaseous phase. So I'm going to pass water at 70 degrees. So initially it is 70 degree, and at some point of time it is at 75, and at the end it is at 80 degrees. And coming to utility, I'm going to use steam as utility, and the steam temperature is 140 degrees. So in this case what will happen is, the temperature of product remains same. The temperature of water is going to vary from 70 to 80, while coming to the utility, the temperature is at only 140. Why? Because we are going to, or we are trying to utilize only the latent heat of steam. So in this case what will happen is, the temperature of steam will remain at a same temperature, but while coming to the product, the initial temperature is 70 and the final temperature is 80. So in this case, if you want to estimate the LMTD, so we have to use, so I'll take it as like the 70 degree as TC1 and the 80 degrees as TC2. While coming to the steam, so it is the same at inlet as well as outlet. Okay, so in this case the LMTD shall be calculated as TH minus TC1 minus TH minus TC2 divided by ln of TH minus TC1 divided by TH minus TC2. Okay, so this is how we need to calculate the LMTD in case where the product as well as utilities are in different phases. Okay, so this is how we are going to estimate the LMTD for different scenarios. So thanks for watching the video. So for more updates you can subscribe, and we got a app for our pharma engineering, so it will be contain so different number of calculations. You can download it from the Play Store. So this is our app, pharma engineering calculator. So it will be having different types of calculators embedded. So recently we have updated our app with the scale up calculators also. So you can download and you can use our app. And if you want any personal training on process engineering or technology transfer, so you can register for our training program at cpetech.co. So you can find the available batches for the training in this registration page. So we are going to provide training in process engineering, process safety management, as well as Lean Six Sigma Green Belt. So based on your requirement, you can enroll for these courses. Thanks for watching the video.